What are vibration modes, and how does mass influence them? Imagine a guitar string vibrating when plucked. It doesn't just vibrate randomly. It has specific patterns called vibration modes. These modes are the natural ways a structure prefers to oscillate when disturbed. Each mode has a unique shape and a corresponding natural frequency. The simplest one, called the fundamental mode, is the lowest frequency and usually involves the entire structure moving in unison. Higher modes are more complex, with different parts moving in opposite directions or with additional nodes where no movement occurs. Vibration modes are like the signature dance moves of a structure. For a beam fixed at one end, it might bend up and down in the fundamental mode or twist in a torsional mode. In three-dimensional objects, these modes multiply, including bending in multiple directions and twisting. Each mode shape is associated with a specific natural frequency, which is how fast the structure prefers to vibrate at that shape. Mass plays a big role in these vibration modes because it affects the system's inertia. When you increase the mass of a structure, it becomes harder for it to accelerate or change its motion. This resistance causes the natural frequencies to lower. Think of it like trying to shake a heavy object versus a light one. The heavier object responds more slowly. The relationship between natural frequency, stiffness, and mass can be expressed with a simple formula. The natural frequency is proportional to the square root of the stiffness divided by the mass. So, if the stiffness stays the same and you add more mass, the natural frequency drops. Conversely, reducing the mass raises the natural frequency, making the structure vibrate faster at its natural modes. In practical engineering, understanding how vibration modes work and how mass influences them is essential. For example, in machinery, engineers want to avoid resonance, which happens when operational speeds match a natural frequency, causing excessive vibrations. By adjusting mass or stiffness, they can shift these frequencies away from the operating range. In buildings and bridges, analyzing vibration modes helps ensure stability under wind or earthquake forces. Adding mass or changing structural properties can alter these modes, making the structure safer and more resilient. In vehicles and precision instruments, controlling vibration modes through mass distribution helps reduce noise and wear, improving comfort and longevity. To sum up, vibration modes are the characteristic ways structures vibrate, each with a specific natural frequency. Mass influences these modes by changing the inertia, which shifts the frequencies and affects how structures respond to dynamic forces. Knowing this helps engineers design safer, more efficient, and more comfortable structures and machines.